be released soon, probably tomorrow or Thursday morning. You will do this in teams of 2 to 3. In some few cases, we may allow teams of 4 if you ask for permission, but typically 2 to 3. The competition will close next Tuesday at 2 p.m. and the winners will be announced in class. And then there'll be a report that documents all the steps that you took in the process of doing your competition. That'll be due a couple days after that. Any questions about the CAGO competition? Okay. Yes.
Is that a no for 4 people?
We've occasionally allowed teams of 4, but I mean, if you have a team of 4, why not have 2 teams of 2? We typically would prefer 2 to 3, teams of 2 to 3. I think in my experience, just having managed groups like this in the past, once you get to 4, the logistics of coordination become more of a drawback in most cases than actually having that 4th member. And since we want this to be a collaborative activity, we also want each member of the team to actually be productive in the context of the group. I think 2 to 3 is the norm and the expectation. Okay, so let's sort of take a brief step back for a minute and take a look at what we've learned so far. So we've, by and large, concluded the supervised learning portion of this course. We will still touch on supervised learning in the later parts of this course, but in terms of the fundamentals, we've basically concluded the supervised learning portion. And supervised learning, we've looked at linear models for the most part in terms of thinking about overfitting, loss functions, different types of learning algorithms and optimization algorithms, and we'll touch on probability later on in this course. And then in the last 2 weeks, we've looked at various flavors of nonlinear models, including variants of decision trees and random forests and bagging and deep neural networks. This week, and in fact the next 3 lectures, this week and the first lecture of next week, we'll be looking at unsupervised learning. And many of the same issues will also come up in unsupervised learning, whether we use linear or nonlinear models, overfitting, loss functions, so on and so forth. Okay, so today we'll look at 2 of the most basic versions of unsupervised learning, clustering and dimensional reduction. These methods predate the existence, these methods predate the term machine learning, and one could argue that machine learning sort of adopted them or assimilated them. And many people who learn machine learning these days think of these as learning methods, but in fact they predate machine learning. Okay, so what is clustering? Clustering is the process of grouping data points into clusters. So the definition is a kind of almost self-explanatory. And there are some properties that we would like to preserve with these clustering approaches. First is that the data points within a cluster should have high similarity. Whereas I'm leaving the term similarity a bit vague for the moment. And the data points between clusters should have low similarity. That's sort of the high-level principle that we would like any clustering algorithm to satisfy for some suitable definition of similarity. So let's start with a very, very simple example. So here's an example of data points on a 2D example. And so we have data points. Now, raise your hand if you think there's 1 cluster in this data set. 2 clusters? 3 clusters? 4 clusters? 5 and above? Okay, so almost everyone said 3, and that's correct. At least that was my intention, is to sort of create this toy example where there is, sort of, in some sense, obviously 3 clusters in the data set. Now, how can we, in an algorithmic way, find these 3 clusters? So unsupervised learning is really the study of that question of how does one come up with algorithmic approaches to identify things like those 3 clusters in the data set, especially when the data set is very high dimensional. You can't just sort of eyeball it. And so in unsupervised learning, we're given a set of unlabeled data points. So our training set is not only the x's, there are no y's. So only input features, no labels. And the goal is to find a model that characterizes some sort of hidden structure or pattern in the data. For example, the hidden structure could be a clustering of the data. In some cases, we can interpret this as a probabilistic generative model of the data, though this will be discussed in future lectures. And more generally, we can think of this as a low-dimensional summary of the data. This is sort of the clustering, for example, is a low-dimensional summary of the data that characterizes everything we care about the data, at least if we go with the clustering assumption. So why might clustering be useful? Well, as I mentioned in the previous slide, clustering is a summary of the data. As a simple example, instead of looking at all the data points, we can now just look at a representative example of each cluster to get a sense of what this data set contains. So here is an example from a research paper from a while ago where they did a image search for the word Pluto, and then they used a clustering algorithm to cluster the images. And so each row here are representative images of a cluster of images that you retrieve from the word Pluto. Now, in the third row, we see things like the planet. In the fifth row, we see things like Pluto, the cartoon character, and there are actually other notions of Pluto as well. And from these representative images from each cluster, we can get a sense of the different types of notions of the word, of images that are associated with the word Pluto. So this is an example where clustering is useful. So another way that clustering is useful is that you can think of it as a way of doing some pre-processing of the data before supervised training. If I know that there are 3 clusters in the data, let's say, then I could actually add that cluster ID as a feature to my data set before I do supervised learning. And that could be a very useful feature that could help with learning, especially in the regime where we don't have a lot of labels. Okay, let's move on to a clustering algorithm. This algorithm is based on notion of centroids, and it is exactly the intuition that we all use to identify 3 clusters in this example. This algorithm is called Kmeans. So what Kmeans does is first we have to hypothesize that there are 3 clusters. So if you don't know how many clusters there are, you'll have to use a validation set. But let's suppose that we hypothesize that there are 3 clusters in this data set, and we need to find those 3 clusters. What Kmeans does is first it assigns a random cluster assignment to every data point. Here it's color-coded into 3 colors. So we've assigned a random color or a random cluster assignment to each of the data points. And then what Kmeans does is it computes the cluster center, or the centroid of each cluster. What that basically means is we compute the average location of all the points in each cluster to compute the cluster centroids. And those are the sun symbols denoted in the example. And then given those clustered centroids, Kmeans does an reassignment of the data points to clusters based on which cluster center they're closest to. And that's what you see here. All the data points closest to the red cluster centroid are now assigned as belonging to the red cluster. All the data points closest to the black cluster centroid are now assigned as being to the black cluster, and so on and so forth. And then we recompute the cluster centroids. So we take the new clustering that we've computed, and we compute a new center of mass, or the center of all the data points in that cluster. And now we recompute the cluster assignments again. Recompute the center of mass, recompute the cluster assignments, recompute the center of mass, recompute the cluster assignments, and so forth. And at some point we will converge, where after we compute the cluster centroids and then reassign the clusterings, it doesn't change. So at this point we've converged. And it's easy to check for convergence. So this is the Kmeans algorithm in a nutshell. Let's write it out a bit more formally. So again, we have a training set of just x's. And here's the minimization problem of the Kmeans objective. Little c are the cluster centers. The big C denotes a partitioning of the training set into clusters. So it is a clustering. And the Kmeans objective says, I want to find a clustering and a cluster center of the clusterings such that the squared distance from every data point to its cluster center is minimized. So this is our notion of similarity, by the way. Our notion of similarity is the squared distance between any data point in a cluster and the cluster center. Now, this is equivalent to the variance, a notion of variance of each cluster of the clustering, scaled by the size of that cluster. So if we can minimize this objective, then we are solving the K-means objective. Okay. So the K-means algorithm that I just presented to you in the last few slides is what's called an expectation maximization algorithm. This algorithm will come up in a few places in the remainder of this course, and here's the first place where it comes up. And the basic idea behind an EM algorithm is that it breaks down the optimization into two steps, an E step and an M step. The E step estimates certain variables, assignment variables of the model, and the M step maximizes the parameters of the model. So the M step is very similar to what you see in supervised learning. The E step is a little bit different. And so in the E step, the variables that we can assign are basically the cluster memberships. And so in the E step, we estimate the cluster memberships. So we hold, and what that means is we hold the cluster centers fixed, and we estimate the best cluster memberships to minimize this objective. And that basically amounts to assigning data points to the cluster center that it's closest to because of the objective. The M step is a maximization step. So given all the variables that are fixed up front, let's find a setting of the parameters of our model that minimizes our objective. And what that means is holding the clustering assignments fixed, estimate our model parameters, and our model parameters here are the cluster centers. And so that basically means for this objective, I'm just going to compute the average point of each cluster. That's how I minimize this objective. And for other models, we have other EM algorithms that are analogous of setting some variables that are what we'll call latent, and then given those setting of those variables, do a standard learning algorithm approach. In this case, this learning algorithm is a closed form formula, just like in least squares regression. Any questions so far? Okay. So let's just walk through a little bit more. So in the E step, we hold the cluster centers, the parameters of the model fixed, and we assign a data point to a cluster that has the smallest distance to the resulting cluster center. That's what minimizes the objective function if we hold the little c's fixed. In the M step, we want to estimate the parameters of our model. In this case, it's the cluster centers. And so just like in least squares regression, this has a closed form formula, which is the mean. We could, of course, also do gradient descent, but it's kind of pointless in this particular case, although there are more complicated models where solving the M step requires doing gradient descent. Okay, so given that we've solved this problem up to this point, what can we do with this clustering? Well, we can summarize the data set by its cluster membership. We can say we have this data set is summarized by 3 clusters. Here's a representative data points from this cluster, from each cluster. The clusters seem to be balanced. They're all 3 have roughly equal size. One of the things that's interesting about this objective function is that, okay, if this is the objective function, which is I want to pick k virtual data points such that I can represent all of the data points in my data set with only these capital K data points. Another way of saying that is I want to find the best reconstruction of the data set that I have using only capital K data points. And reconstruction here is measured by squared distance from the true data point to the reconstruction. So if I were to approximate all the red data points as the center of this data set, of this cluster, and all the black data points as the center of the black cluster, and all the purple data points as the center of the purple cluster, then what is my reconstruction error? My reconstruction error is exactly the distance between each of these points and their respective cluster centers. And this notion of reconstruction is one that is often used when deriving unsupervised learning approaches. We want to find a notion of reconstruction such that we can find this low-dimensional representation of the data that is a reasonable reconstruction of the original data set. So just to recap, the K-means algorithm is a notion of centroid-based clusters. So it defines clustering using a notion of centrality. In particular, all the items in the cluster must be close to each other, which is equivalent, if you use square distance, to being close to a cluster center. We solve using an ENM algorithm. There are also probabilistic variants that we'll touch on in future lectures. And this is a useful approach when the centrality assumption is good, but not necessarily a good approach when the centrality assumption is bad. And so just to illustrate an example, and this next example is admittedly a bit extreme, but just to illustrate the point, we'll look at another example where the centrality notion may not be nearly as as useful. So to do that, here's a thought experiment. Here's a data set, and I've given you two clusterings. One clustering has 2 clusters. A second clustering has 7 clusters. Raise your hand if you think the black clustering is a better representation of the data. And raise your hand if you think the orange clustering is a better representation of the data. I see that most people have abstained. And in some sense, that is probably the wisest thing to do. It really depends on your use case, right? There seems to be perhaps a notion of hierarchy of clusterings in this data set. And no single clustering captures everything that we may want to analyze. So to illustrate this point more concretely, we'll look at an alternative to centroid-based clustering, which is linkage-based clustering. So linkage basically means that we want to find, we measure similarity by how closely one clustering is linked to another clustering. And I'll just simply illustrate this using this algorithm, which is called agglomerative clustering. So the first thing we do is we find the 2 data points that are closest to each other. And that's these 2. And we'll call that a little cluster. And then we do this process again. So now we found the next 2 data points that are closest to each other. And this process continues. And now, at some point, we realize, OK, actually, the closest 2 data points is actually a data point connected to a data point that already belongs to a cluster. So now what we've done with agglomerative linkage-based clustering is we say, OK, these 3 data points now form the next clustering unit. And this process continues. Where we keep connecting the 2 data points that are closest to each other that are unconnected, and we join all of their, by transitivity, we join all of the clusterings, all the clusters containing those 2 data points into a single bigger cluster. And so on and so forth. And so this is agglomerative clustering. So if you've taken an algorithms course, you'll know that this is equivalent to finding the minimum spanning tree of a data set, also known as Kruskal's algorithm. In fact, the two are equivalent. The order that the edges are added defines the cluster hierarchy. And so if we want to sort of find a clustering at a certain level of granularity or refinement, we can actually look at the clustering hierarchy and take a cut of that hierarchy to define a clustering at the granularity that you desire for your data analysis. So if I want to summarize data sets into 3 clusters or 4 clusters, and I want a notion of hierarchy that I can sort of transition up and down while I look at the data sets, then this is a great way to do that. Okay, so just to recap on clustering, it is arguably the simplest instance of unsupervised learning. The goal is to find a clustering structure of the input features. We could do centroid-based clustering, which is, by the way, the most common form, the most popular form, or linkage-based clustering. And we simply use the parameters of the clustering to form a summary of the data set then, and we can inspect the data set by using only the summary statistics given to us by the clustering, such as in K-means clustering, we could just look at the cluster centroids or data points close to the cluster centroids. And these methods work great when the clustering assumption is good. There are instances where the clustering assumption is not so good. So let me give you another example. But before I do that, any questions about clustering? Yes?
Yeah, how do you know when to stop the agglomerate clustering? Maybe you said it.
Well, typically when people do agglomerate clustering, they do it to completion. And then you get to choose what granularity you want to view the clustering at. So in some sense, all the clusterings in the hierarchy are quote unquote valid. Which one is useful depends on your application. So if I really just need to look at 2 clusters, I need to break it into 2 clusters, I keep it at 2 clusters basically, right? And if I decide I want to zoom in and break it down, I can break it down.
But you have to go through all the points first. All points have to belong to.
Yeah, I mean it's just Kruskal's algorithm. It's very fast. Yes.
Is there any relation between the 2 clustering algorithms? Like, for example, would a K-means clustering always be achieved by the other?
Oh. Yeah, I think in this very toy, clean example, Kruskal's algorithm and Kmeans' algorithm will give you the same result at a certain level of the hierarchy in this very clean example. But when the example gets messier, I don't think they'll give you the same result. Kmeans doesn't have a notion of hierarchy. So for stuff that looks like this, it's hard for Kmeans to give you the same result. For example, Kmeans made this decide to do something completely different here. Okay, so